to this meeting. I wish I was in Montreal now. I thank especially David Croydon and Makiko Sasada for the invitation. Okay, so we will talk about box-ball systems, statics and dynamics. And this is joint work with Chi Nguyen, Rolla, Minmin, Wang, that is in the meeting now, and Davide Gabrielli. So as explained in the previous talk, Takahashi and Satsuma introduced in 1990 this system that in the previous talk, Professor Takahashi explained how it works. But we have a box it's a one-dimensional system. So we have boxes Z in Z. A ball configuration is a configuration 0, 1 to the Z. And eta of Z is equal to 0 if the box is empty and equal to 1 if it is occupied. And there is a carrier that is visiting boxes from left to right. And the carrier picks balls from occupied boxes and deposits one ball if carried at empty boxes. So here we have a small simulation. In the first line, we have the configuration eta with the balls in ones. This is the position of the carrier. So the carrier arrives at this box. So we are thinking that there is only a finite configuration here. So the carrier arrives empty with this box, it carries the box and then deposits in the next box, obtaining this configuration after the deposit. And then the carrier picks another box and another ball, and it cannot deposit it here because it is occupied. So it will carry another ball here that is picking this one, and then it deposits it here and then here. And the carrier is, anytime that there is a 0, the carrier decreases by 1. So T eta will be the configuration after the carrier visited all boxes. And here is the formula for this iteration. So the carrier increases 2 eta of x minus 1 is 1 if eta of x is if there is a box, and 0 if it is not. So this will be 1 if there is a box at eta, and if it is 0 or minus the 0, the carrier will be empty because it's not carrying anything. Well, as was explained in the previous talk, this is motivated by the KBV equation that is here, and that has the property that it has a solitons that are solitary waves that propagate with little loss of energy and retain shape and speed after colliding with other walks. So here you have time like that, and here you have an initial configuration for this equation that is evolving. So there is a big soliton that is traveling at speed faster than the small soliton, and they do some mess in the collision, and then each one reappears with the same shape and speed after the collision. Professor Takahashi explained it with an updated picture like that. What is the connection between the discrete and the continuous picture? I will not dare to explain that. There are a lot of papers. I quoted some of them here. And but it's much better to go to the origin of that. This Professor Takahashi talk. So I will just say that there are a lot of work on that. I just am quoting here some mathematical works. I was motivated by a talk that gave Zug here at Buenos Aires some years ago, and where they were studying with Professor Kato and Tsujimoto a spectral decomposition of a symmetrized BBS in an interval with a carrier capacity 1. But there are a lot of papers by Levine, Liu, and Pike with studying the static picture, so the size of the big solitons in semi-infinite intervals. And then there is some work by Kuniva now with one-side multicolor solitons, but also later the Kuniva and collaborators, they have a generalized hydrodynamics and for randomized solid BBS. There are a lot of papers by Croydon and Sazada where they discuss the invariant measures and the relation with these dynamics with the Pitman transformation. And finally, they have also a paper with generalized hydrodynamics. And all this is related, as we saw before, with the toda lattice. And so the toda lattice has a generalized hydrodynamics is very similar to this one. I have some work with my co-authors in generalized hydrodynamics, but this will be explained by our co-author Minmin Wang, that is in the meeting on Thursday. It is useful to use this work representation that is classical in interacting particle systems. If you have a configuration eta here, you can think that eta is in some sense like the derivative of some path, so the discrete derivative. So this is connected with a path that I will call C of eta, that is going down when there is a 0 in eta, and it's going up when there is a 1 in eta. Okay, so these zeros here means that the path is going down, the ones up, and zeros down, etc. Okay, this is a bijection if one fixes the origin of the path. If not, there are, of course, all vertical translation of the path give the same eta. It's like the derivative and the integral. Okay, so an important thing to understand here is the concept of record. So we will see later that it is important that if we consider an infinite configuration with infinitely many balls, in some sense you have more empty size than balls, because if not, the carrier will get an infinite load, and then that would mean that you have just to flip the whole configuration. So we are taking configurations with less balls than empty sides. That means that the path C is essentially a decreasing path, and there are, for all I, height I, there is a first time that the path visits the site I. And this will call the site minus I. And this will be called the record I for the path psi. Okay? The concept of record is important, so please, if it's not clear, let me know. Okay, so if, and then we will call excursion the piece of path that is between two successive records. For instance, here I have a record here, and I have another record here. So the excursion will be this piece of configuration.
Excuse me, there is a question.
Yes.
Yes, just very quickly, when you say that there are less ones than zeros, well, the thing is Z, so it's doubly infinite. Do you mean that there's a finite number? You mean there's a finite number of ones and an infinite number of zeros?
No. It's to be precise, you can compute the density to the left and right as you sum the number of ones in a box of size n and divide by n, and you ask that there is a limit when n goes to infinity to some lambda, and I mean that lambda must be less than 1/2.
So is it that there's, when you say there's a finite density, is it that there's a saturation on the left and on the right, where either it goes to all zeros or all ones, or is it?
No. You have a density that lambda that is, so you have a proportion of ones that is less than 1/2, but you have conversion. I will talk a bit later about this. For the moment, it's just informal.
Okay. Thank you.
It's okay? Yeah, thank you. Okay, so if I have an eta in 0, 1 to the z, I define, so this is an infinite with infinite many balls. I define t eta of z equal 1 minus eta of z times 1 is z is not a record. So I flip all the particles, all the boxes that are not record, and the records that keep them as zeros. Okay, so if you have the configuration eta, you can describe also to know if some box is a record, because the configuration C is just a sum of the partial sums of eta, and and then you can do that. So if in terms of the path, when you do that, if you have all the records, what you do is just to flip to flip the excursions down. This is also defined when there are not all the records, but it's not fun, because if there are no records, then you just flip all the configuration. Okay, so if you consider the dynamics of the work, as I said here, and I continue using the notation T for the operator, T of the path C of box Z is just two minimum of the local minima of the path minus C. So this is a 2m minus x from Pitman transformation. This was introduced by Pitman in the 70s. And then you can see also in the GAL, but this is a famous transformation, and you can, and this was Croydon and Sazada who discovered this relation between the two things. Of course, they didn't realize that this simple transformation was as rich as presenting all the solitons as we are studying now. But there is a paper, for instance, of Hamblin, Martin, and O'Connell that used this Pitman transformation to show that the box-fold system, so the increments of the path, if they are independent, identically distributed with density less than 1/2, so the density of occupied boxes, then the measure is invariant. And this is retaken then by Croydon and Sazada that proved a lot more of invariant measures for these dynamics using the same reversibility ideas as here. But they use it also in these two papers. They also proved it for the case of Markov chains and others. Okay, so the Pitman transformation gives you more information than the evolution of the ball configuration, because the Pitman transformation gives also a motion, a down motion that you cannot see in the ball transformation, and this down motion gives you the number of balls. If you take the configuration at time z, the configuration z, and then you evolve the path t units and look at z again, you will see that you have the flow of balls crossing the point z between time 0 and t. So, the flow. So in this configuration, you can see the current of the flow of balls. So you can also take the speedband transformation and follow the record of the configuration, starting with configuration xi at time t, and this will be the position of the ith record of tt of xi. So simply what you do is you come, if you have here position I, if you have position I here, and then record at time 0 was this one, time 1 will be this one, okay? Record I. This will be record I at time 0, and this will record I at time 1. I will see another picture later. Okay, so the soliton motivation is when you observe or you simulate the evolution of this system, you see that when you have an isolated block of 3 ones, for instance, and you evolve, the carrier comes picking the 3 ones and put in the 3 zeros here, following the 3 ones. So I painted blue the 3 ones that are the origin of the balls at time 0, and the 3 zeros where the balls will go at time 1. So you see this, and you see then that if you have 3 balls in a row, they will go at velocity 3. So at the next time you will see again 3 balls in a row. So you can think that this is a soliton that is traveling at speed 3. And then if you put another soliton of size 1, that will be this one, you see that there is a collision, and then you will see, after the collision, you will see the 3 balls and the 3 solitons here and the 1 soliton here. Okay. Okay, this is the same picture, but I put the records as a dot just to see the solitons more clearly. And then I put this picture that was done by hand, but where in some sense we learned from it what was going on. So I have 2 blocks of solitons of length 2. These are 2 solitons, and these are 1 solitons. And then you see this configuration here is the same as this configuration here, just translated after the collision. And this is the collision between these 2 blocks in some sense. So Takahashi and Satsuma proposed a way to identify solitons that I will repeat fast now. So you can run the segments induced by the broken lines of the work. So this will be an infinite run, then you have another run here, another run. Okay. See, yes. So the idea is that you explore, so this is an infinite run and this is an infinite run, okay? You explore runs from left to right and look for the time that the run that you are looking at is smaller, that has length k, is smaller than the following run, okay? Then you come here and you see that this run here is smaller than this. And then you take this run and the same number of boxes of the next run, that is this one, and call it a soliton, okay? And then you have this red soliton. Okay, now you pretend that this red soliton is not here. And in this case, you will have an infinite run here. You will have a 4, 5, 6 run here, okay? Continue here. You just identify this point with this point. And then this is a 5 run, then the other one is infinite. So what you do is just identify the second soliton, that is this blue one. What will be these 5 boxes here plus these 5 boxes here. Okay, so it's important to to describe. So a soliton is a K-soliton is a set of 2 K boxes. K of them are ones, and the other K are zeros. And but also they are numbered, so they are labeled H1, HK, the head of the boxes that have ones, and T1, TK, the boxes that are in the tail, that are the zeros. Okay, and it could be that the tail is before the tail. In this case, the tail is before the head, and in this case, the head is before the tail. Okay, so the head is the part that is going up, and the tail is the part that is going down. And I call the support, I call gamma soliton. The support gamma is the set of boxes that belong either to the head or the tail of the. Okay, so if you have an infinite configuration that has all records, that means that all excursions are finite. And then you can apply the TS algorithm to each excursion that I said is whatever is between 2 records, pretending it is isolated. So you assume that the records, the right record and the left record belong to infinite runs. And then all the points in the excursion will, all points will be either a record or belongs to the support of a soliton. All the points in the excursion, all the boxes in the excursion belong to the support of a soliton. Okay, now we have this proposition that is in some sense already contained in the work of Takahashi Satsuma, that says the following, that for any configuration in X is the configurations, I forgot to put it, with finite, with density. Okay, the density is the proportion of boxes, of occupied boxes divided the number of sides divided n. So it's, and taking n to infinity to the left and to the right, and they must coincide. I will call this lambda. Okay, if eta has a soliton gamma with tail T of gamma equal to A, that would be a vector with K coordinates. This will happen only if theta, so at the next time, we have a K soliton gamma prime with the head in the same points. So you can see this here, that this is the configuration eta, and the other is theta, but these 2 lines are the same. I just put it down just to differentiate the soliton. So you see that the tail of the blue soliton is this one, coincides with the head of the blue soliton at time 1, that is this one, okay? And the head of the red soliton, that is this one, coincides with the tail of the red soliton in the next, with the head. The tail of this soliton coincides with the head of this. So the tail of the red coincides with the head of the red at step 1. Okay, so here I just have a simulation with soliton conservation where you can see that that this head is coincides with this. This is a tail and head, the tail and head. Then you have then a tail here and head, tail and head, and so on. Okay, and you can look at all the solitons satisfy that condition. We have a theorem proving that it's not. It's pretty involved. Okay, now I will describe the components. So this is that is a soliton component that is based in a notion that is called slots. And so you have to look close to this picture here and say, I have a 3 soliton that is this red one, and a 5 soliton that is this blue. And the 5 soliton has these are the head 1, this is 2, 3, and 4. This is head 4 of the tail of the 5 soliton. And then after that, then I have this head 5, okay? Well, when this happens, and then you have these 3 soliton here. When this happens, I say that this 3 soliton is attached to the head, to H4 of the 5 soliton. Okay. And then a K slot, just quotation mark, is a box where K solitons could be attached. See that if you try to attach these 3 soliton, for instance, at H3, and you put it here, in fact, you will get 3 soliton here that will be attached to this record, not to the soliton, okay? Not to the 5 soliton, will be attached to the left. So here are the 4 possibilities to attach a 3 soliton in 5 soliton. You can do it at H4, at H5, and T4, and T5. So now you have to do the exercise and try to put a 3 soliton in any other place in a 5 soliton, and you cannot do that, okay? So to attach a soliton means that you will put a K soliton in. So if you want to attach a soliton at slot X of an M soliton, you put the K soliton at boxes X plus K minus 1, and then shift by 2K the configuration to the right. So that means that you put it here. You have originally this, sorry, like that, and then you put the red thing here and put this part there. Okay, so I am claiming that you can put the 3 solitons after at those points, and here I have a definition that says that box X is a K slot if either it is a record or it is in the tail or head of a bigger soliton gamma with M bigger than K, but also the L must be bigger than K. So the index of the tail point or the head point must be bigger than L. That is what happened here, no? Because I am attaching a 3 soliton, I can do it at H4 or 5 or T4 or T5, okay? So let's try to put the 3 solitons, 3 slots here. So I have a record here. So 3 soliton will be here, okay? And then I have this is a 4 soliton, the blue here is 1, 2, 3, 4. So I can attach it at H4, that is this. And then I can put it at T4. Then there is another 4 soliton here, and I can put it at H4. And then at T4, that is this. I mean, when I put the box here, I mean that I can attach it here, okay, to the left. Okay, so what happened here, I have a configuration eta here that took a path C. From the path C, I have the Takahashi Satsuma identification on solitons. And once I have the identification of solitons, I can go at each box and see where it belongs to, and from there construct slots of all size. So I put the slots of size 3 that are the green ones, okay? then slots of size 2 that are red, and then the size 1 that are violet. Okay, and then I have the following, that records are k slots for all k, and then the other records are simply h will be htl or hl for L bigger than k. So I will have k slot for all TL of gamma, HL of gamma for gamma bigger than k, with a size bigger than k, and L must be bigger than k. Okay, so let me call the SK of theta the set of k slots of theta, and of theta the set of records. And as you can see in this picture, you have that the k slots are contained in the k plus 1 slots. Okay, so they are contained. Okay, once that you have the slot identified, you fix the 0, call a slot 0 for each one of the sizes. And here I have an infinite number. And then you enumerate each line independently. So in each line, I have 21 slots enumerated from 0 to 20. Then here I have 11 enumerated from 0 to 10, and then 5 from 0 to 4, and I have only 1/4 slot enumerated 0. Okay, record 0 is a k slot for all k. Okay, once that I have identified the slots, I will say that there is L k solitons attached to k slot number I if the support of this L solitons belongs to the segment with extremes k slot I and k slot I plus 1. I have a slot 0 here for 4, slot 0, 4, and I have 2 4 solitons between a slot 0 and here I have a slot 1 for 4 is this one. I have a slot 4 here because this is a record. This is a slot 1 for 4. Okay, and then these 2 blue 4 solitons are between records 0 and 1, or between 4 slots 0 and 1, so they are attached to a slot 0. And then this can happen for all solitons, all colors or sizes. So I will have an array zeta ik that will give me the number of k solitons attached to the k slot number I. Okay, for instance, here I have that zeta 17 1. This is here. This is one slot. This is one slot number 17, and I have one soliton between 17 and 18. So zeta 17 1 is 1 in this case. Okay. Okay. So the slot decomposition of ball configurations, I have I have for this picture I have this piece of the matrix. Okay. Okay, if you want to do the slot decomposition of infinite ball configurations, we perform the slot decomposition of each excursion, but then you continue the enumeration. So the next, after this, there is another excursion, but then you continue with number 21 for the slots, for 1 slot, and with number 11 for 2 slots, on number 5, etc. Okay, and then to the left you do the same. Okay, if you do that, you will have an infinite array that for each pair slots slot label k size, you will get the number of k solitons attached to the ith slot. And this I will call the mk component of eta of I will be zeta of ik. And what I call the slot decomposition is this matrix, infinite matrix. Here I is in Z, and K is just the soliton number. So I have an infinite matrix, numbers 0, 1, 2, etc. in all the space. Okay, so the map here is the way that you do the map. So suppose that you have the configuration here. There are 4 excursions that are, I am calling them epsilon minus 2, epsilon minus 1, epsilon 0, and epsilon. And then these excursions. This is 1. This is minus 1. This is 0. This is, and minus 2 is just this piece here is empty, minus 2 configuration. So you put this big number here will give you this piece of the picture here. Then the next configuration, this gives you this piece of the picture here, the next excursion. Then the negative excursion, the big negative excursion gives you all this. And the 0, this empty excursion gives you a column of zeros here, and then 0 everywhere. So they occupy one place, but they are all 0. You can invert this this equation, but I will jump this part. You can if you have this configuration, but without the lines separating them, you can start exploring this first line, look for the maximum here, and then construct down this triangle. And from the triangle, you construct the first excursion. Then you ignore all this triangle or put all the remaining part, you put always, you push it to the left, and then you do the same. You look for the first one, that will be this one, and then you can construct the second excursion and so on. Okay, this is what is explained in this picture. Okay, so it is important to consider the evolution of the target record. So I have level 0 here, and I have the record 0 for an initial configuration. And then if you evolve this configuration, record 0 is jumping to the left. Okay, so I will consider now a dynamics that is looking at the system as seen from this record 0. And this next theorem that tells that if you look at the component, you have this picture. So you have a dynamics here for the configuration C, and then at each time I can write down the array theta, or array M of eta. And what is claiming in that theorem is that the array that you will find at time 1 for a configuration eta will have that the rows of the array will be translation of the original rows. Okay, this is what I mean here, that the component evolution is hierarchical translation. So I need a couple of notation. I have not much time. So the record 0, I have already defined the record 0. I have already defined the record 0. At time t is the minimum z such that t eta of z is equal to 0. We saw that in the simulation. And then I'm looking at the process as seen from record 0. I need also to know the flow of m solitons through record 0 that are solitons. Since I can identify the record 0 and the solitons, I can tell how many m solitons have jumped through record 0. And then those solitons carry slots, so I can also compute the flow of k slots through record 0. Okay, so the theorem says the following, that if you take a configuration C that has record 0 at the origin, and then I consider the dynamics as seen from the record 0 at time t, then the dynamics, the k component of this configuration as seen from record 0 is a shift of the k component of C. This theta represents here a shift, and OT of C represents the number of slots that jump through record 0. And then there is this K of T moving. So this is the component of the configuration at time 0, and this is the same the K component at time T. And you see that this is a translation of this K component by KT plus the number of K slots that jumped through records. The key element of the proof here is that you can show that the number of K slots crossing a given K soliton in one iteration is exactly K. This is what gives you this part of the translation. Then you need only to control from record 0, which is the number of the record of the slot of the 0 slot at time 0, because since the slots have jumped through record 0, you have messed up the notation. Okay, so this is an important theorem. And here is a simulation. So I have a ball configuration that is very simple. It has only 4 solitons. And the components are these 4 here. Here, since we are looking from the left, there are no solitons crossing record 0 that is fixed here. And I can see that just they collide there, but the components move as if nothing happened. They don't realize that they are colliding. Okay, so can I use more for 5 more minutes, maybe?
Yes, okay.
Okay, it's just because I'm missing this theorem. Okay, so the previous theorem tells me that your dynamics, also the BBS dynamics, is just a translation of each one of the components, but the translation of each component depends on the configuration of the components that is strictly bigger than the K component. So the translation of the K component depends on components M for M bigger than K. So that suggests that if you have independent components, then you should have an invariant measure, independent components and horizontal shift invariant. So this is what says the theorem that we proved in that paper with Nguyen, Rolla, and Wang. Say that if you take an array zeta that with independent lines that are horizontal, shift stationary horizontally, each row, and has a finite mean when you look at the column. So you look at the total number of points in any column, and then call mu hat the law of the configuration that will have this array as transformation. Then the obtained measure is invariant for the process as seen from a record, from record 0. This measure will be also record invariant. That means that if I jump to the next record, I will see the same distribution. And if I do the palm -1 of this measure, I will get a shift stationary and T invariant measure. So this is a way to construct a T invariant measure. Well, I have no time to talk about the proof, but I think I will finish here. Thank you very much. Sorry for the...
Thank you so much. So if you have a question or comment, yes, please.
Sorry, you talk to me now?
I don't know, this is maybe not related to your talk, but there is this equation which gives the effective speed of the soliton. Do you have a kind of proof or understanding of this effective speed?
Yes, we have a theorem about the effective speed that will be explained by Minmin Wang on Thursday, and this says it's the same. It's very similar to the generalizer hydrodynamics for other systems also, like the Toda lattice or the Harrod system.
In general, it's kind of guess. In this model, you have a really precise proof of that speed.
You have a precise, you have a explicit expression. Well, you have a system of a linear equation that the speed must satisfy, and you can show that in fact, you can show if you have an invariant measure with independent components, and each component is independent also, is IID, then you can compute the law of large numbers for a tagged soliton or quasi-particle, and will go to the effective speed of that case, that size. So if you have a k-soliton at time 0, and you condition to have a k-soliton at time 0, and you look at time t at its position, divide by t, this will converge to the effective k, let's say.
Yeah. Hi. Thank you very much, Makiko. Yeah.
Hello.
Hi. Hello. So I have a question about the characterization of invariant measure, especially for this theorem now on slide. So it must be independent under some condition, or so do you know some necessity of independence?
No, Leo Rolla has some examples where you have in the periodic things that are
you said.
Yeah,
okay.
You arrange it like a puzzle. You have to arrange the solitons in such a way that after 2 or 3 steps you get the same configuration. Invariant. So no, the answer is no. Okay,
so some more condition maybe you tried before, so some mixing condition, or
yes, we started with that, guessing that mixing conditions, but we couldn't finally prove really that mixing conditions should be sufficient to because the case that the examples of Leo are ergodic but not mixing.
And more especially, there's a class that as you said, so every sites are independent for each line in solitons, and this can be characterized in terms of some ergodicity or some strong notion of ergodicity, or so it seems it's generalized to Gibbs ensemble, but that
I'm not sure. I don't know really, but in the next talk I will talk about how the product measures satisfy this condition, that they have independent components and they are IID geometric, the entrances.
Okay. Yeah. Thank you very much.
You're welcome.
Thank you so much. Okay. Is there any question? If nothing, okay. Thanks again to the speaker. Thank you. Thank you so much.
Thank you.
Yes.